Hi, it's a video for the equations of uniformly accelerated motion, also known as the SUVAT equations. I'm going to show you how those equations are derived and give you an idea of how you use them. Your task is to try and learn how you derive those equations as best you can and have an idea of how to use them, so that when you arrive at the lesson we'll be able to get straight on with some worksheets, some problems involving those equations. So at any point, just stop the video, go back over anything that you didn't quite understand, and make sure that you have the best idea of what's going on as possible by the time you arrive at the lesson. Okay, so this video, you're meant to watch it before the lesson, not after. Alright, so let's get started. The derivations of the equations all centre on a graph. So let's describe the motion that we're talking about here. We are talking about a car that starts at a velocity. Let's give it some positive velocity, and we'll call that velocity u. So it starts at u, and that is at time t0. So that's the time that we start at is going to be 0, and it has velocity u. This car has constant acceleration, and it ends at a velocity of v at time t. So that's the type of motion we've got going on. It's a velocity time graph, so maybe you could already plot that graph. So if I just start you off with the axes vt, okay, so that's just meaning v for the axis and t for the t-axis. So there's our graph. Remember, it starts at a velocity of u, it ends at a velocity of v, and it has a constant acceleration. So perhaps you could plot that graph. If you know how to plot that graph now, then stop the video and plot the graph. So this is a little hint here. You should have a piece of paper and a pen ready to do some work whilst you go through this. Okay, so if you could do it already, you may have plotted it already. Now I'm going to give you a hint, if you haven't been able to do it yet. Remember, this is velocity here, so if you know you're starting at a velocity, then you can plot it on the axis and start from there. And also, it's a constant acceleration. So for a velocity time graph, the gradient of the graph shows you the acceleration. So therefore, you know that the gradient is constant. And because I said it has a constant acceleration, the gradient is the same at all points, and it's positive because it's accelerating, it's acceleration. So now perhaps you could plot that graph. It's got a constant gradient, starts at a certain value along this axis and finishes at a certain value. Okay, remember, it starts at t0, ends at tt, time of t, it starts at u, ends at v, so try plotting it down. Okay, so hopefully you got something like this. U, this is v, that's 0, and that's time t. Okay, so that's our graph there. You don't need to have the repeated v's and t's there really in this case. We'll just focus on that. Okay, so that's the graph. We might also want to put a dotted line there, just to indicate that's where the u is. That helps later on. Okay, so that's our graph there. Now, we've got 4 equations that we need to derive. So we're going to start with equation 1. At each point, what I'm going to do is tell you what we want, the aspects of the graph that we're going to use to get it, and then tell you what I want the equation in terms of, and see if you can derive it yourself from the graph. Okay? At each point you should write down all of your working, so it should be clear that you have actually derived it from the graph and not just copied it out of the textbook. So what we're going to do here is we're going to use the gradient of the graph, because the gradient tells us the acceleration. So if you could write down an equation for the acceleration And then, so you get an expression for A, and then you rearrange it so it's in terms of V. That's how we normally state the first equation, in terms of V. So if you can do that now, try that now. If you need a little more information, then remember that acceleration is the rate of change of velocity. It's the rate of change of velocity. Maybe that's enough for you. If it's not enough for you, rate of change means that it's the change in the velocity. Okay, so we've got two velocity values here. The change in velocity over the change in time. And we've got two time values here. So now you have hopefully enough information to derive that equation. Rate of change of velocity, which is the change in the velocity over the change in time. So that's equation 1. This is what you should have done, okay? So equation 1, the expression for A is equal to V minus U. The change in velocity is it ends at V, but it started at U, so it's V minus U. That's the change there, okay? Delta V is V minus U. There. And the change in time is T minus 0. Now if you just wrote T there, that's fine, because T minus 0 is equal to T. So V minus U over T. And then I wanted that rearranged into, so that V was the subject, so V is equal to A times T, and then added on the U. So U plus A T. Okay, that's our first equation there. On to equation 2. So what I want here is an expression for the displacement S. We want an expression for S, and you're going to need to substitute into that the expression for V minus U from equation 1. So we've got equation 1 up there. You hopefully got it on your piece of paper too. So you'll need to make a substitution of that. So you'll have an expression for S. That's what we're going to end up with as well. So we don't need to change the subject of the equation. But you will need to make a substitution from this equation for V minus U. Okay, so if you can do that now, try that now, using this graph, remember. So try that now. If you need a little extra help, that's fine. Displacement for a velocity on the velocity time graph is the area under the graph. So this is our graph line here. That area under there, that gives you displacement. So maybe you could do that now. Remember, we want an expression for S, but then you're going to need to make a substitution for V minus U from that equation. Okay, so try that now if you can. Okay, this is a little more challenging, so here's a little bit more information. If we're going to do the area under, look, this is why I put this dotted line in here. Look at the shapes you have. You've got a rectangle here, and you have a triangle here. So if you find the areas of those two shapes and add them up, you'll get your expression for S. So you look at the dimensions of the shapes that are given to you there. Try using those and see if you can do it now. Okay, hopefully you're able to do that. Here is what we were looking for. Okay, so we're working out the displacement, it's the area under the curve. So we're going to work out this bit first. Well, this is a rectangle, area of a rectangle, one side times the other. So S is equal to UT. This is the rectangle. Okay, that part. And it's plus this triangle. Well, this is T. Oh, T minus 0, remember, is equal to T, and U minus 0 is U. Okay, so that's why I've done that. Anyway, going back here, it's T times V minus U over 2. So it's half of this because, right, the area of this rectangle would be T times v minus u. Okay, so that there is v minus u. That's what that length is. And then this triangle is half of that. So plus a half v minus u times t. Okay, so that's our expression there. I'll just put in that that's our triangle component. I then said we need to substitute for v minus u from equation 1. V minus u is equal to at if you rearrange that equation. So we're going to substitute that in. Okay? And there we get our second equation, s equals ut plus a half at squared, because it's at times a half t. Great, that's equation 2 done. So we've done 2. Equation 3. This is actually the last equation where we work directly from the graph. You'll see what I mean when we get to equation 4. So, equation 3. I want an expression for s again, but this time what you're going to do is use the mean velocity. So that the displacement is equal to the mean velocity times the time. So try working that out now, that equation. S, you don't need to change the subject, it stays as S. So mean velocity times the time. Okay, if you need a little more help, let's look at our velocities here. Let's get rid of this bit now. Okay, we've got 2 velocities, u, v. If you want to find the mean of those, u plus v divided by 2. So that's your mean velocity. Okay, so you should be able to do equation 3 now. Mean velocity times the time. Right. Okay, equation 3 then, mean velocity times the time. So the mean velocity is u plus v divided by 2. And the time is t. Okay, so we've got that. Just tidy it up a little bit. S is half u plus v times t. If graphically speaking, what we've just done, the mean velocity is right in the middle of these two, straight line. So what we did was we did u plus v over 2. Did that value multiplied by this, and we got the area underneath this fine dotted line here. So you can see that area of that small triangle would fit in there. So we've got that same area as we had before, graphically speaking. Alright, so we now have 3 equations. 4th equation then. This equation, as I hinted to earlier, we don't actually work directly from the graph. What we do here is we take 2 equations and we eliminate one quantity so that we have an equation with different quantities to what we've had previously. Now I want you to notice something, that all 3 of these equations have one quantity in common. In fact, they have 2. It's not the u though. Okay, so you see each equation has a u. They have another quantity in common, and what we're going to do is eliminate that quantity. So if you can spot which quantity it is, and you can do that straight away, the equations you need to use are equation 1 and equation 3. Okay, so these 2 equations, use those equations, eliminate that common quantity, the one that isn't u, and see what you get in that case. We want to have this in terms of v squared. All right, v squared is what you need to use. So try that now, if you can do that. Okay, the quantity that we need to eliminate is t. See, all three equations, they have a t in them. Well, we want an equation that doesn't have t in it. And that means that if we have a problem where we're not given t and we don't need to find t, then we can use that equation. That's the reason for doing it. So now knowing that you need to eliminate t, maybe you can do it now. Equations 1 and 3. Okay, if you need a little more help about how to do that, you can use simultaneous equations. One way that I find easiest to do this is rearrange that equation so that t is the subject, rearrange that equation so that t is the subject, and then if both equations equal t, then you can make the equations equal to each other. So try that. Okay, so now I'll show you how to do it, if you haven't yet been able to do it. Okay, so we're combining equations 1 and 3 to eliminate t. So, rearrange this equation. So t is going to equal v minus u divided by a. And that will be equal to 2 times s divided by u plus v. Because that would be rearranging this equation for t. So we have this. Now what we need to do is cross multiply these terms. So then we get v minus u times u plus v, or v plus u, equals 2as. If you're familiar with the SUVAT equations, you probably recognise this 2as bit. Alright, let's multiply these out. So we get vu, so vu plus v squared minus u squared and minus uv, or vu, equals 2as. Okay, so we've got a vu minus vu, so those cancel out to 0. Then we've got plus v squared and minus u squared. So what we'll do is we'll take the u squared over to the other side. So then we have v squared equals u squared plus 2as. So those are our 4 equations, the SUVAT equations, or properly the equations of uniformly accelerated motion. So those are the derivations. You need to know those. You could be asked those in the exams. They often come up. This one's quite a popular one, actually. So be aware of how to do those. Now, what about how you use them? Okay, the idea is each equation has 4 quantities, and therefore you can use an equation. If you have 3 of the quantities, you can use it to find the 4th quantity. So let's say equation 1, v, u, a and t. If s is given to you and 2 other quantities, you can't use that equation. But let's say u is given to you, a is given to you, and t is given to you. Well, you can clearly see you've got that, that, and that. So therefore, you can solve for v. You can find out v. If you were given s, u, and a, and you need to find t, you could use this equation here. So you're given that, that, and that. You can solve it for t. It's a tricky one to solve for, but you could do it. So you get the idea. If you have given 3 quantities, solve for 1. Alright? best method here, whenever you're doing a problem involving constant acceleration and where you're given three quantities, bear in mind as well that the quantities are not always explicitly stated. It might say a car brakes to a halt, so therefore V equals 0. Yeah? So if it brakes to a halt, therefore V equals 0, because the final velocity is 0 because it ended at 0. Or dropped from rest, therefore U equals 0, because when you drop it from rest, starting at 0. So the best method for solving problems involving constant acceleration is to write down SUVAT, be methodical about it, write them all down, then go through the question, identify what values were given to you. Was S 100 meters? U was at 0. A was 9.8. V is what you need to find. T was not given to you, you don't need to find it either. So which equation do you need to use? If you have SUVA, you need to use this equation over here, and we need to find V. So keep it in that form and put the values in, find the answer. Perhaps instead, let's say S was the one you needed to find, U was 0, and this was 15 meters per second. Okay? So in this case, same equation, but now we need to find out what S was. So we need to rearrange the equation for S, then put the values in. So we write down S equals V squared minus U squared over 2A, then put your values in and solve for that. Right, so that's the principle of how you use the equations. What I'm going to do now as well is add in a video link to an experiment that links to this. It's the experiment to determine the acceleration of free fall using a metal ball bearing. So I'll add that link in and you can watch that video as well to see an experiment based on this. And that's it for today.